Let's talk about the unsung hero of our digital lives, the physical layer. It's the part of the network we can actually touch, and believe me, without it, absolutely nothing else would work.
I mean, have you ever really stopped to think about it? How do the ones and zeros that make up an email or that cat video you just watched, how do they physically get from one place to another? We love to talk about the cloud, but data doesn't just float, right? It has to move.
Well, the answer is right here. It all happens at layer 1 of the OSI model, the physical layer. This is ground zero. It's where the abstract digital world meets the real physical world of cables, connectors, and even the airwaves around us.
Okay, so how in the world do we get from abstract data to something physical that can actually travel? Well, it's all about translation. Think of it as a two-step process for teaching our data to speak the language of hardware.
Step 1 is what we call encoding. You see, a computer doesn't just blast out a raw stream of ones and zeros. That would be total chaos. Instead, it converts that stream into a very specific, predictable pattern. The best analogy? It's kind of like turning letters into Morse code, a system of dots and dashes that both sides have agreed on beforehand.
And that brings us to step 2, signaling. So if encoding is figuring out the Morse code, signaling is actually tapping it out. This is the magic moment where those encoded patterns, those dots and dashes, get transformed into actual physical energy. We're talking electrical pulses, flashes of light, or radio waves. And this just perfectly illustrates that whole flow. You see, it starts up at layer 2 with a packet of data called a frame. The physical layer grabs that, encodes it into that special pattern of ones and zeros, and then, bam! The signaling process turns it into a physical wave all ready to hit the road.
And what that signal actually looks like totally depends on the highway it's traveling on. If it's going through a copper cable, it's going to be an electrical pulse. If it's shooting through a fiber optic cable, we're talking about a flash of light. And if it's wireless, it's a microwave signal flying right through the air.
So let's talk a little more about those digital highways. There are really 3 main types of physical media that carry pretty much all of our data today.
And you're definitely familiar with all 3. We've got our good old copper cables, like the Ethernet cord plugged into your computer. Then there's the incredibly fast fiber optic cable, which is really the backbone of the entire global internet. And of course, wireless, the radio waves connecting our phones, our laptops, you name it. Now, copper has a bit of an Achilles heel. Because it uses electricity to send signals, it's really vulnerable to interference from, well, other electrical things. We call this electromagnetic interference, or EMI. And it can come from almost anywhere. Fluorescent lights, big electric motors, even a nearby radio can cause problems. Fiber optic cables, though, they are a total game changer. Why? Because they use light instead of electricity, and that makes them completely immune to all that electrical noise. Now, they generally come in 2 main flavors. You've got single mode, which uses a laser to shoot light in a perfectly straight line for incredibly long distances. And then you have multi-mode, which uses cheaper LEDs for shorter runs, like connecting buildings across a campus.
And this table really shows you the classic networking trade-off, cost versus performance. Your standard copper cable, what we call unshielded twisted pair or UTP, is super cheap, but you can only run it for about 100 meters before the signal fades. Single-mode fiber, on the other hand, can go for thousands of meters, no problem, but it's going to cost you a lot more. It's always a balancing act.
So think about it. With all these different cables, different signals, and tons of different companies making this stuff, how is it possible that a network card from one company can talk to a switch from a completely different company and it just works? The answer, and really the magic of the physical layer, is standards.
Yeah, these big international engineering organizations, think groups like the IEEE and ISO, they set rules that govern 3 key components to make sure everything just plays nicely together right out of the box, right?
First, they standardize the signal itself. This means every piece of hardware agrees on exactly what a 1 looks like and what a 0 looks like. Whether that's a specific voltage level or a particular frequency of light, it's a universal language that everyone speaks.
Next up, the connectors are standardized. Just think about that common Ethernet plug, the RJ45. The standards define its exact shape, its size, what each one of those little metal pins does, and that's precisely why it fits perfectly into any laptop, router, or wall jack, no matter who made it.
And finally, the cables themselves are standardized. The rules dictate exactly what kind of copper or fiber to use, how the cable has to be built, and what kind of performance you can expect. This is huge because it lets all those different companies create their products with total confidence that they're all going to work together.
And this, right here, shows you why those standards are so critical, right down to the millimeter. Getting the physical details right isn't just a suggestion, it is everything. I mean, look at this. Just untwisting a tiny bit too much wire when you're putting on a connector can create enough interference to absolutely kill your network's performance. The details really, really matter.
All right, let's wrap this up by zooming out a little to really appreciate why this fundamental layer is so incredibly important.
Every single thing we do online, from streaming a movie to managing the entire global financial system, is built on this physical bedrock. Without these carefully engineered wires, fibers, and radio waves, our digital world would literally just cease to exist.
And that's what makes Layer 1 so unique. All the other network layers are really about software and logic. They're just code. But the physical layer, this is where it all gets real. It's implemented in the actual silicon, the copper, and the glass that physically connects our world.
So, I'll leave you with this thought. The next time you're on a video call with someone on the other side of the planet and it works flawlessly, take just a second to think about the incredible physical journey your data is taking. A perfectly orchestrated dance of light and electricity, following a precise set of rules and happening at nearly the speed of light. It's pretty amazing when you think about it.